Welcome back to ECE 320A. Homework 2 is due in a week. I believe that's correct. Should be due on Tuesday of next week. And exam number 3, I wish. Exam number 1 is due or will occur next Thursday on the 9th of February. And that will cover material in chapters 10 and 11. Today what I want to do is finish up the power factor correction example. I think last time we finished with determining the capacitor value. Let's now see what that provides in terms of information, or what that tells us. We will then get into chapter 11, which talks about three-phase power. We'll briefly go over the benefits, why we want to worry about three-phase power, or why it's important to do. We'll look at the system structure, what pieces are in a three-phase power system in a very general sense. We'll then talk about balanced three-phase voltages, what that means. Then get into some interconnection options, and one of those interconnection options will be a Y-Y circuit, and hopefully that will make more sense when we get to that point today in the lecture. And you need to be able to analyze and work these Y-Y configuration networks. That's one of the goals of chapter 11, and we'll talk more about that as we progress. Let's begin with the example from last time. In which we had a couple of loads. You should have this information from last time's notes. That's why I went ahead and just copied it down or rewrote it again here, and we can quickly talk about it. Load number 1 had real power of 48 kilowatts and a particular power factor of 0.6 lagging. Load number 2 had a real power or an average power of 24 kilowatts. Its power factor was 0.96 and leading. We were supplying these two loads with a voltage magnitude in RMS of 500 volts. That's supplying those two loads. What we want to do is figure out how can we select a capacitor in order to correct all of the reactive components on that side, on the load side of this configuration, so that the source effectively sees a real load. That capacitor is to be designed to get rid of the net lagging behavior of the load, or the net inductive behavior of the load. Questions on that? And in the process, we will find some of these values indicated in red. And in particular, hopefully we will see that after the power factor correction, the I sub G, the supplies current, you'll see that its magnitude diminishes considerably. And we'll hopefully, and that's a good thing, because now if you have any losses in the line, you've minimized those losses by correcting the power factor. That's the point of this power factor correction. That's our system. Let's look at this or analyze this maybe differently than what we did the last time, because there's all sorts of ways that we can analyze these systems. There's many different ways to find the same answer. Let's look at load 1. What we are given is the real power, and we could write that as the voltage magnitude and the current magnitude of that load times the cosine of the angle theta sub 1. And what is theta sub 1 really representing? That's the difference in phase between the voltage phasor and the current phasor. And you might pick one as a reference, you might pick another one as a reference, but once you've picked a reference phase, you live with that, and theta 1 would then be defined or determined by the relative distance in angle between the voltage phase and the current phase. That's what theta sub 1 means in this case. Or you could say that this is V1's magnitude, I1's magnitude, and those are phasors. I maybe should indicate that with a bar. Cosine of theta 1, we're actually told that in the form of a power factor. So we know, what do we know in this first equation that I've written down? We were given the real power. We know P sub 1. That was 48K kilowatts. We know the magnitude of our voltage supplying that load. That's 500. We know the power factor, PF1. We have one equation and one unknown. We should be able to find that, and that's our current. That's the magnitude of the current, I1, flowing through that load, load number 1, as we've indicated here. Meaning we can now solve for the magnitude of I1, and that's simply going to be P1 over V1 power factor 1. And P1 over power factor 1, last time we simply called that the apparent power. So there are all sorts of ways to write or find these expressions or quantities. This was 48K, this was 500, and this was 0.6. If you do the computations, you end up with the magnitude in RMS, the RMS magnitude of that first load's current is 160 amps. That's what's needed with the 500 volt supply voltage to produce 48 kilowatts of real power at a power factor of 0.6. Questions on that? That should be fairly clean. Now from that we can find actually the total power of, or I should say the complex power of load number 1. Again, I'm doing this in a different way maybe than I did last time. We can find the angle. We can actually explicitly find that angle theta 1. Since the cosine of theta 1 is the power factor, we can invert that expression and end up with 53 degrees. What's the sine on that angle? If the voltage phasor was at 63, where's the current phasor? Behind it. And it's behind it in an amount such that 63 minus that angle is equal to 53. Right? The difference in phase between the voltage phasor and the current phasor is 53 degrees. It was lagging, which tells us then that the angle here is a positive angle if you're looking at the complex component of your complex power in this expression. This is because of the lagging nature of your load. Once we have that angle, we can now compute the reactive power using a similar formula that we've just used, except now we're looking at the orthogonal piece to the apparent power. This is then in the vertical direction. We're looking at the sine of theta 1. We now have 500 times 160. Now we know what I1 is. Sine of 53.13 degrees. and that ends up being 64 kilovars for Q sub 1. Or the complex power is 48 plus J64 kVA, written in rectangular form, real part and reactive part. That shouldn't present a problem, finding that information from the given values or quantities specified in the problem statement. We were given exactly the same information for load number 2, and because of that, we can now use the same equations, just different values. What's V sub 2? It's the same as V1. They were in parallel in this particular example. So we have that. I'm making sure that you're awake. That should have been I sub 2, not I1. Those loads were not in series. So this is V2 I2 cosine of theta 2. If we now solve for I sub 2's magnitude, given the information that we have, this is 24 kilowatts. V2 is V1 is 500. And the power factor was 0.96. This ends up being 50 amps. The previous load 1 was how many amps? So you could sort of see the relationship between the amount of complex power for each load just by comparing those currents, since the voltage is the same. You can say, wow, the first load is demanding more than 3 times the current as the second load. Load 1 is the big consumer in this particular example. Theta sub 2, what's its sign? It was leading, and for that reason, we can put that minus sign into our expression. This is now the inverse cosine of 0.96, and that ends up being minus 16.26 degrees. Not a real big angle, so we're not using that much reactive power in this particular second load. Q sub 2, again the same formula, and if we plug the numbers in, we end up with minus 7 kilovars. Again, this should be presenting itself because we know that that load was leading. And we now know, if we were asked what S sub 2 is, the complex power of load 2, that was 24 minus J7 kVA. Questions on those two loads and how we found that information? Now that we have that, we can find the total complex power. And how do we do that when these are in parallel? It doesn't matter, does it? That's why I said that. They could be in series, they could be in parallel. You just add these complex powers. The total power then, complex, is P1 plus JQ1 plus P2 plus JQ2. And we've already found all of those pieces. It's the two P's, 48 plus 24, and the algebraic sum of the Q's. The total power then is 72 plus J57 kVA, total complex power. What we want to do, as indicated in the original schematic, is to introduce a capacitor to annihilate that reactive piece of the complex power. We're wanting that Z sub C to effectively produce the same amount of reactive power, just opposite to what it presently is. In this case, it's going to be supplying those magnetizing bars. Right now, the two loads are consuming or using 57K magnetizing bars. We want to supply that with the capacitor. Let's then add this capacitor. To give us the power factor correction. That's our formula for impedance of a capacitor. Now we have to be told or know what the frequency was. In this case, it was 60 hertz. That was given. We multiply that by 2 pi, a little more than 6, and we end up with what we conveniently call 377, and that's times C. That's the impedance, and what do we want, or what do we need? We need minus J57. But do we need that from this, or what is supposed to be giving us the minus J57K? What's that? What are the units on that, and what are the, well, this is an impedance. But what we need is we actually need this impedance to give us some reactive power, which is a little bit different than just the impedance. Yes? Now we have to use a formula that we want to use, the one that I'm thinking of. The generalization that I'm using is to replace I with its Ohm's law equivalent, V over Z. And in this complex form, what's the complex power? It's V times I star. We need to star that I expression, which is V over Z. V times V star is V squared. And we're now dividing by the impedance, conjugated. We now have 1 over J377C in the denominator, meaning that J377C comes upstairs with a change in sign because of that conjugation symbol, where we now have this is minus J omega C V sub C squared, and that's supposed to be the minus J57K. We now have the appropriate formulas, and the only unknown, once we realize that omega is 377, and what is this piece? That capacitor's in parallel with all the other loads. This was 500, and now we can solve for C. this is what we wanted. Making that equality hold forces C to be 605 microfarads. Now, if somebody says, okay, what's the, with the power factor correction incorporated, what's the total complex power in formulas or in terms of variables that we've already defined? Okay, it's S1, S sub 1 plus S sub 2 plus S sub C. And S sub C was purely reactive, wasn't it? So in this case, S sub 1 and S sub 2, we had already defined to be S sub T, and S sub C can be replaced by Q sub C. Since Q sub, well, maybe I'm abusing notation a little bit, but I guess I called that Q sub C before, so that's okay. Maybe I shouldn't have done that because usually we have J Q sub C. Does everybody understand what I'm nervous about now? If I said what was S sub C, I might be calling that P sub C plus J Q sub C. And here I've actually incorporated the square root of -1 into Q sub C. But hopefully you can get over that particular notational flaw in this discussion. What is the corrected complex power? It's completely real now that we've annihilated that inductive piece of the original total complex power S sub T. What's another way of writing S corrected? Or what if I said this? Does that make it, now that should give you a hint as to what I'm trying to find. The apparent power is the same in this case as the complex power because it's just one piece. We don't have to worry about the two orthogonal components of the complex power, but if I explicitly indicate that the apparent power is what I'm looking for, what do you know defines the apparent power in terms of variables in the circuit? It's the power of the source, it's the apparent power of the source, and how would you compute that? It would be V sub G times I sub G, those magnitudes, right? Because we know that S in general looks like that. If we now looked at the magnitude of S, we get that. That's what I want to use. Now I can say that I have the apparent power of the corrected system now looks like the product of voltage in RMS and current in RMS. I know the left-hand side, that's 72K, and I know half of the right-hand side. I still know V sub G. That's what my source is supplying. That's the 500. If that's the case, the magnitude of the supply current is now 72K divided by 500. And if you compute that, you end up with 144 amps. If you're really paying attention, There's something that hopefully should be shouting at you. If you look at the magnitude of the supply's current, or the source current, and suppose we just compare that with load 1's current. What was load 1's current? What have we done wrong? You buy all my arguments? What in the world is going on? Does everybody understand what I'm trying to get you to see, first of all? If we go back to our diagram that we began with, the source is only being asked to supply 144 amps in magnitude. That's now going out to these loads where we really have three loads. We have the capacitor's impedance giving us a load. We have load 1 and we have load 2. Load 1 actually needs, as far as an amplitude of current, 160 amps. Load 2 required 50 amps. And we're being able to deliver both of those with a source that's only supplying 144. Does everybody see sort of the interesting issue that's going on here? So how can we explain this, or how can we justify this, or how would you explain this to your parents? Now they're looking at their utility bill and they go, our power factor is 0.6. You have a big plant. You have a big house if you're consuming that much reactive power. But we won't go there. Maybe you have a lot of machines that you're playing with. What is happening is that the loads and that capacitor that we introduced, that was what we were trying to do, are exchanging stored energy. What are we doing? We have this magnetic field that's expanding and collapsing, and load 1 wants it, load 2 wants it, load capacitor is giving it back and forth. They're just trading it, but they're trading it down at the plant side. And the source doesn't really care what they're exchanging back and forth at the plant side, and it's a good thing, because now we've really cut down on the magnitude of the current going across the transmission line supplying those loads. So the loads and the capacitor are exchanging stored energy via, let's just call it reactive currents. And these reactive currents circulate between the loads and the capacitor. And they do not have to follow, or they do not have to flow these reactive currents. Those currents do not have to flow across the lines from the source to the loads. And if the power company is there metering their particular current and using that in product with their voltage, their supply line voltage, they're not seeing the power demand that you would naturally want to present since you've now introduced this capacitor. Your plant has flipped in these capacitors and changed the reactive component of the load so that the power company sees you as effectively a real load. That's now lowered the current that has to supply from the source out to those particular loads. And that's a good thing. Questions on that example and that concept? Yes? Since we lowered the current, the question was, since we lowered the current, we effectively lowered the power. That's correct. Now, if you looked at the apparent power from the source when you didn't have that capacitor in place, and now I've forgotten, maybe you have it in your notes. What was did we calculate I sub G, the magnitude before? I was thinking of that when I was lecturing, and I forgot what we had done before. I'm sorry? So we went from 184 amps to 144 amps. That's significant, or that's a significant difference between the uncorrected and the corrected version of the load. Now if you stuck a resistor in there, which you're doing by these transmission lines, you now have to push 144 amps instead of 184 across that resistor, which is your transmission line, and you're going to have much less loss, and you could compute the apparent power from both particular configurations. And now it's the difference between V sub G, 500 times 184, and V sub G times 144. Am I using the right numbers? It's buried. But yes, you're asking for less power now since you've corrected with those capacitors. Obviously, you would have to buy those capacitor banks and flip those into play so that you could now have to, or be able to save some on your power bill or on your energy bill. Yes? So now we have not really, so the question was, if we shut the power off, so now you turn off the switch, can that capacitor supply our loads for a while? What's that capacitor doing? Or would it help you in terms of your end result? The capacitor is not really giving you any real energy or real power, correct? It's just supplying the reactive piece. So you shut the power down, you're not going to be able to do any useful work at the plant. That may circulate around, but you're not really getting much for that. That's just sort of the reactive pieces are playing together, maybe effectively, but you're not seeing any real work coming out of that. So you turn the switch off, you're done. Okay? You're done for the day or the week or whatever. You no longer want to manufacture, apparently, if you turn the switch off. Questions on that? But we are concerned about these, well, power factor correction, as I was jokingly saying before, at your house, you don't need to do that. You guys don't have capacitor banks, do you, at your house, where your mom goes out and flips a switch and says, oh, our power factor is a little low, let's correct it. She's texting you PF, and you'll go, you need to have that PF equal to 1, Mom. Right? And she goes, okay, I've got it. And she flips in the capacitors appropriately. Well, that may not be necessary at the home. Why is that? What's your home look like? What does it present to the power plant or to the power company? You look mostly like a resistor. Now, if you have a huge air conditioner and some other heavy loads that are heavy in machines, your power factor may not be 1, but the power company usually doesn't worry about that. The industrial plant needs to worry about that. And what we are concerned with now, going into chapter 13, are these huge drivers of energy or demand. We want to know, how do we push these big blocks of energy around in the United States or across the town to supply some industrial load? And in that case, we are not going to be doing it with single-phase power. We're going to be doing it with three-phase power, and now what we want to do is figure out what that really means, or what are, let's say, the benefits of three-phase power. And I'll try to outline 3 sort of major ones. And you'll hear people talk, maybe in the power industry, of moving large blocks of power. And if they're doing that, is there any difference between those power lines and the lines coming into your house? You're probably not getting kilovolts into your home, right? So this is accomplished using high voltages. What are we after? We're after power. Power is V times I. But what does I do? If it's going down the transmission line, I squared R. We want to minimize I. Well, if we have a certain amount of power, V times I, if we make I small, we can get the same power if we make V big. So now that we've increased the voltage considerably, we don't have to push the current, as much current down the line. We need to get it there with this high potential, but that now allows us to maybe reduce the I squared R losses in our system. Maybe I'm getting ahead of myself. Let me just say that we want high voltages. And what are these 3 phase? Phase means it's alternating, doesn't it? It's AC. And it's fairly easy to convert AC from a low frequency to a high frequency. If you look, I don't even know, a lot of these now are done more electronically than the old-fashioned way, but a lot of these these ways of converting from AC down to DC to power something typically used to have a transformer in them. And that transformer allows you to convert high to low or low to high without any moving parts. If it was DC, then we would have to do something a little bit more extravagant. If we had high DC lines feeding our, let's say, DC loads, we might want to drop them down. Well, with AC, we can obtain high voltages using transformers when the voltage is AC. Isn't there a transformer movie? Oh, that's something else, isn't it? But you get the idea, right? You have these cores and you have coils of wire, and that can be used to either step up or step down voltage, and that's a transformer. Versus if we had DC, we might have to use rotating machines, and those are more expensive maybe than these coils of wire. Using rotating machines to raise and lower the voltage. meaning one of the benefits of moving large blocks of power with AC sources is we now have a less, maybe I shouldn't say that word, there insert complicated, less complicated, because we are going to have complex. We have real and reactive pieces, but we have less complex systems, or a less complex system for raising and lowering voltage. That's one benefit. Second benefit, well, this is maybe if we now have less current than if we had one, so essentially three-phase you can sort of think of, oh, we're splitting this up into three pieces. Now each line is delivering 1/3 of what one other line would have had to do if we were just doing it with one line. So now we have three lines and a neutral giving us the same power, bulk power, that we had with just one line. And because of that, if we have less current flowing on each of those lines, we don't have to spend as much in the cabling. We can have smaller cables. So we have smaller, lighter, let's say just components in general, than with the single-phase networks. I'm also listing performance as a benefit in addition to economic under item 2. I'm not sure how I decided to rank these as 1, 2, and 3. But performance, we now have, well, let me just write it down and then I'll try to explain it. We now have a steady torque, or a more steady torque, supplied to machines. Meaning, if we just had a single phase, now we're going high, low, high, low, high, low, and what did we see was happening to our power, our instantaneous power? Do you remember what was happening to that? It was going up and down, wasn't it? Up and down, and it was doing it at twice the frequency of the voltage and current. With three-phase, what we can actually see is when we have all three phases going, we now have a constant power flow moving. Each phase is oscillating, but once you add those three phases together, you now have a constant, steady flow of power. If that's the case, now we're supplying that to a three-phase machine, and that machine is just nicely, smoothly spinning. Instead of saying, oh, go high, low, high, low, high, low with the machine, and it's trying to respond, and it gets a little rough. Now we have a smoother supply on these machines, leading to less vibration and a more efficient system in general. Finally, what we will talk about is something, this is really what we will focus on, and that's balanced three-phase power. And we'll talk more about that pretty quickly. But if we have a balanced three-phase system, then we will show in a few minutes, hopefully, that the neutral conductor when it's going to be carrying all three currents. If it's a balanced load, all three of those currents are going to sum to zero. They're going to vectorially combine to give us zero, and now we're not going to lose any power in that neutral conductor. Since we're not losing any power, that's an economic reason. Let me now say that no power, no I squared R loss, or let me say no power lost in the neutral conductor. And if we are working with balanced, if you understand balanced three-phase power, you've gone a long ways in understanding the more generic case, which would be an unbalanced system. Because a lot of times unbalanced systems are analyzed using balanced operation. So let me just say that some unbalanced conditions, and the easiest way to think of something being unbalanced, if we have a three-phase system, we are now saying that the three sort of components of the load look exactly the same. Now you could sort of, just in a very crude way, you could say, okay, that's like putting three hair dryers in each, one hair dryer in each phase. Well, now somebody says, oh, I don't need my hair dried, I need to charge my cell phone. So now two phases have hair dryers and one's a cell phone. Well, that's unbalanced. Is that making sense? That unbalanced load then presents more challenging analysis concerns, but in general, if you understand the three-phase balanced or balanced three-phase, you are a long way in going towards being able to solve or analyze unbalanced load conditions. Some unbalanced conditions can be solved by what's called in the power system terminology symmetrical components. And that symmetrical components analysis relies on understanding balanced operation. And that's what we are going to focus on or think about in this class, is balanced three-phase power. That's chapter 11. There may be a few problems that deal with unbalanced, but you'll know how to solve those or what to do in that case by learning what we're talking about here. Let's look at a block diagram of this three-phase system. First, we have our three-phase source. Then we have each phase, we have three phases, and we'll call those an A phase, a B phase, and a C phase, and we have the neutral conductor, so there's four lines. We have the A phase relative to the neutral, the B phase relative to the neutral, and the C phase relative to the neutral. We have four lines feeding the load side. But what happens between the two hair dryers and the cell phone? What happens to your in between your three-phase load and your three-phase source? If you travel around and you look up and you see these big lines flying or located in the distance, what had to happen in order to get to that high voltage? Transformers, probably. You now have to raise it up, and you have to step it down to supply these loads. In between the source and the load, then, is some transformer configuration, or transformers. And obviously these big things that seem to buzz. Do you remember that? Or have you ever stood near some of these wires and they sort of hum? Or maybe the equipment or the machines. This is now what you can think of in terms of chapter 11. This is the big picture view. We have three-phase sources, three-phase load, and we have this stepping up and stepping down and transmission in between. But typically, you know what WLOG is? Without loss of generality, we can basically omit this middle piece and not have to worry so much about it in terms of the transformers. We may model the impedance of the transmission lines, but the transformer stepping up and stepping down, will probably not worry so much about that. We want to get the concept, and so WLOG, without loss of generality, we can do that by neglecting some of that that's going on inside the middle box. Let's now talk about balanced. Now that we have the picture, let's look at balanced three-phase voltages. And I will simply draw some vectors to begin with, and your drawings can be a little bit more accurate than mine probably. But let me draw voltage A. So that's V sub A. Now, what am I doing? I'm interested in a 360 degree or 2 pi picture. And I want to split that in a balanced way. And if I want to now divide 360 degrees or 2 pi equally into 3 pieces, so hey, now we've got a pi and I get a third of it. Wow. So if you think of a big pie or a cake, maybe you prefer cake, but if you wanted to share that equally, how big would your pieces be? How big is that wedge? 1/3 of 360. So if we divide 360 by 3, what do we have? 120. Now I need to split this V sub A. I'm going to say, okay, here's V sub B, and that should be the same length, and it may not be, and its angle is supposed to be 120 degrees. V sub C, supposed to be the same color. At least I can get the color right. I may not be able to get the angles right. And this is now V sub C. These are all phasors. And the way that you can think about this is, what's happening to the A phase? It's actually spinning in real time at a frequency of omega. Well, if A is spinning at omega, B is spinning at omega, and C is spinning at omega. But typically we don't draw the spin, we just draw it at a given snapshot in time. And if we took a snapshot and we snapped it right at when V sub A was at 0 degrees, this would be at minus 120, this would be at minus 240, but typically we don't like to go that big. We usually like to stay within 0 and 180 degrees. So we refer to this as V sub C, or this at an angle of plus 120. Is that making sense? And that's now how we would write this. We would have V sub A as a phasor is some magnitude. Let me say it's V sub A n, and I won't put a bar on it, at 0 degrees. And this is the A phase voltage. V sub B, shouldn't change color, should I? Slowing me down. This is now V sub, well, you know what? Let me just call that the same so that you know. Let me just call that V sub M. And this is now at minus 120, and V sub C now, this will really get you. What do you think that particular phase sequence is called? Where did positive come from? I'm impressed. That's a positive phase sequence. Did everybody see that? It's upbeat. It's positive. You can't see that? That's the ABC phase. That's a positive. No. This is the positive phase sequence. Or, if these are spinning around, if they were spinning around, we could actually walk in this direction, and what would we see as we walked from the A phase? We would see B, then we would see C. So the positive phase sequence could equivalently be called the ABC phase sequence. You could have called it the positive phase sequence or the ABC phase sequence. Now I think you can anticipate what's going to happen. That's one particular set of balanced three-phase voltages. They're the same magnitude, they have the same length, and they're 120 degrees apart. And we see A, B, C if we were going in this clockwise direction, if we were walking in a clockwise direction. Question? Well, it was there a minute ago. Somebody's asking about that subscript on the V sub A. I saw it, I really did, but it disappeared. There's some magic going on. I lost that blue smoke, magic blue smoke that Dr. Marcelin talks about in 220. But my blue smoke was an M, a subscript. Question? Does that help? So those are supposed to be the same magnitude, 180 degrees, or 120 degrees apart. Now the next one that we want to look at is conveniently called the negative phase sequence. Or the ACB phase sequence. That's the negative phase. And now that I've labeled it that way, I think you can sketch it without too much more help. There's VA, there's VC, and there's VB. And now we hit ACB, ACB. Or if we were standing still and this was spinning counterclockwise, we see A, then we see B, then we see C. I'm sorry, we see A, then we see C, then we see B. Negative phase sequence. And that has exactly the same Now, what you don't want to do is you can't put a positive phase sequence and a negative phase sequence together in parallel. If you have loads, they all have to be working together. You have to have a positive phase sequence or a negative phase sequence if you're putting loads together in parallel or sources together. So the circuits can operate in parallel only if they have the same phase sequence. Now, what I want you to do in your class participation for today, so here's your ICP. I want you to tell me what the result of adding these three pieces ends up being. What's the sum of V sub A plus V sub B plus V sub C? That should have taken you just as long to figure that out as it was for me to change my batteries. Yes? If you do you need about 20 more minutes to solve that? I'm really just taking attendance with this in-class participation. If we have a set of balanced three-phase voltages, if you simply sketch those head to toe, or toe to head, toe to head, toe to head, if you put V sub A, now you attached VB to that vectorially, then you attach, so you attach the tail of VB to the head of VA, and now you're going down in a positive phase sequence. Now you attach the head of B to the tail of C, and where do you end up? You better end up where you started with the toe of A, if it's balanced, if you sketch things properly. Meaning if you now have a balanced three-phase system, V sub A plus V sub B plus V sub C is 0. And what is V sub A, V sub B, V sub C bar? Well, it's not quite that. But what is it? If I said V sub A bar, what is that in terms of a description, or describe that, or tell that to another faculty member? What is this quantity? What would you say you're working with? That's a phasor. So this is true for phasors. What happens if I said, well, take V sub A instantaneously, V sub B, and V sub C. So now this is the instantaneous voltages, VA, BV, V sub B, V sub C. What's that going to be equal to? Still 0, isn't it? Because what do the phasors tell you? They tell you the magnitude and the angle. You can insert those into this cosine omega t formulation. And now V sub A is related to VB related to VC in this same balanced manner. Instantaneously, these voltages are, when added together, 0. And that's a good thing. Now your neutral conductor is flat all the time in terms of current flow if you have a balanced set of voltages. Now, we know what balanced voltages look like. How do we connect them? Well, that shouldn't be a 2 period. It should just be 2. There are 2 ways to interconnect. Let's just look at voltage sources for now. One way to do it would, for me to get the A phase, let me say this is V sub A, V sub B, and V sub C. Meaning coming out here I would have the A phase, coming out here I would have the B phase, and coming out here I would have the C phase. And this point I might label as N. You're going to have to use your visual and mental capabilities now. That's actually called a Y connection. So if you stand on your head, you can see the Y. Yes? It's just conventionally drawn this way, sort of upside down. But hopefully this you can see, if you inverted that Y, you can sort of see, oh, that's the configuration of these sources. That's a Y configuration. That's one way of configuring or interconnecting these sources. The other is to put them together in the following way. Oh, and look at how they are connected. All of their negative terminals are connected together. And you have the positive ends coming out to give you the A phase, the B phase, and the C phase. Now if you read down from top to bottom, oh, it's A, B, C. If that was a positive phase sequence, that would make nice connection with the positive phase sequence. Another possible way of interconnecting these sources is to say, oh, here's my A phase. Here's my B phase. And I'm going to call this, because it's the positive terminal of A, I'm going to call that my A. This is the positive terminal of B. And what do I know about this point right there? If I was doing it consistently, this would be the C phase, and that's now C. What Greek symbol do you think we use to denote this connection structure? Delta. So this is a delta connection. And if we actually put a neutral conductor in there, and that's N, can you see that the voltage across A to N is not the same as A to B? And when we're going to call these, we're going to start calling a lot of different, using a lot of different terminology. We're going to talk about line voltage. And when we talk about line voltages, what I'm really saying is line to line voltage. Meaning, if I was in this configuration, it's pretty easy. Where's the neutral conductor? There isn't any. What's my line voltage? Well, that's the voltage between A and B, or B and C, or C and A. over here in the Y configuration, my line voltage could be from A to B. My line to neutral voltage would be A to N. So we're going to have different things going on. We can have our phase, so our phase voltage here would be V sub A. And it would be from A to N. That's our A phase voltage. In the delta configuration, and so the phase voltage here is not the same as the line voltage. Does everybody see that? You could just write KVL, and determine what V sub AB was by using KVL in a mesh. The line voltage, the voltage from A to B, is not the same as the phase voltage V sub A. Down here, in the delta configuration, what's the A phase? Well, that's the line voltage. Do you see how I can really get you confused? Here the phase voltage, and this will make more sense as you look and start discussing these more, but be thinking about all the different possibilities of what happens when you're playing with these different interconnections. Now, what I left off of, if these are sources or generators, drawn without generator impedances. What I should have done to make them a little bit more realistic is to actually put an impedance there, maybe a resistor and an inductor. And I would have to put the same impedance into each phase to make it a balanced set. If I now said, well, what would that impedance look like? It could be this resistance, which we might call winding resistance in a generator. And this might be then this JX sub W, which is our inductive reactance. And if we have generators or motors, they're going to have all these coils of wire, and it's going to look inductive in nature. And that piece would be introduced or inserted into each of those source voltages series combination in that diagram to make it more realistic. But I left it off just so that you could explicitly see the delta and the Y. Now, that was just the source side of our big picture, where we have our source, transmission lines and transformers, and our load. What do you think happens at the load side? Two hair dryers and a cell phone, right? If it's balanced, we have 3 hair dryers. But how are the loads configured? How do we interconnect the loads? They can be Y or delta. Now we get to talk about our combinations. If I have loads or sources that can be in one of 2 configurations, and I have loads that can be in one of 2 configurations, how many possible combinations do I have? 4. So now I have 4 possible arrangements for sources and loads. And that's why we call them the way that we do. We could have a Y source and a Y load. We could have a Y source and a delta load. We could have a delta source and a Y load. Or we could have a delta source and a delta load. And what we will start on next time is looking at the fundamental circuit, which is the Y-Y combination. Our source is a Y configuration, the load is a Y configuration. What does that give us? If we can analyze that configuration, we can basically convert back and forth to be able to do anything we want of these four. I'll see you on Thursday.